nice find.
Okay, so here's the next big unit. So the third 9 weeks, we're going to cover 2 big ideas. Acid-base equilibrium, and then redox, okay? And those are the 2 big, like, yeah.
How many more tests do we have before I actually would.
So there's going to be one
I'm
more big
guessing-
test over redox,
Okay.
and then a midterm final. Yep.
Is there a lab part?
It depends on the timing. Don't know yet.
So probably no lab.
Not yet. We've only had the 1 snow day, so don't know. Okay. So 1 more big test. Okay.
Okay.
All right. And then fine. I guarantee you we're going to have
Would
a
the
final.
midterm
I
go
promise
in-
you that.
Would the midterm go in as like a test grade?
Yes.
Or-
Okay. So when you have redox, there's a couple of things that are important. Number 1, if you look on your periodic table, on the back of that periodic table, there is, and this is going to be your friend and your go-to thing. There's what's called a reduction potential on the back side of this, okay? This is going to be your absolute go-to source for things relating to redox, because there was a tremendous amount of information from the redox. So first off, we have to figure out what the terminology is. So redox is short for reduction and oxidation. So how I always learned it, and as it appeals to me since I spent a lot of time in Africa, is that Leo the lion says go. Okay? So that's my go-to method for remembering redox reaction. So that stands for lose electrons, that's oxidation. Oxidation. And if you gain electrons, that's reduction. So you see kids on the redox test going, Leo says go, Leo says go, Leo says go. Now, but there's a couple of things that's the very simplified definition of this. The short version of this is that redox is just a battle for chihuahuas. Who wants the chihuahuas more? Okay, literally. Redox is just the movement of the chihuahuas. Okay? And when you rearrange the chihuahuas, you get different things. Now, it's always going to be a battle for who wants the chihuahuas more. Okay? So basically, if you have something willing to give up the chihuahuas, that's okay, that's being oxidized. But notice these are called redox reactions. These aren't reactions, there aren't reduction reactions, there aren't oxidation reactions. Okay? It's a reduction oxidation reaction. So something has to lose the chihuahua and something has to gain the chihuahua. If there's no rearrangement of the chihuahuas, that doesn't mean there isn't a chemical reaction. It just means that it's not a redox reaction. Okay? So this chart, these are all reduction reactions. Okay? That's why it's called a reduction potential chart. And so basically, if you look at all of these all involve something gaining chihuahua. It might be 2 chihuahuas, it might be 1 chihuahua, has a certain value to it. So if something's going to be involved in a reduction oxidation reaction, something is going to win in the tug of war. Okay, so let me give you a simple example. So here's a reaction that you've always seen before. Whoa, don't need that one. Let's see. It's a relatively clean one. So I'll take some hydrochloric acid. Now, the reason that we study acid-base equilibrium is so that we understand what's going to happen with hydrochloric acid. So this looks very much like water. Okay, can't tell the difference. But here's what's going to be important. And I know I've stressed this before, and I'm going to stress it again as vitally important to really understand what's happening in a redox reaction. You have to understand what's happening at the atomic level. So I'm going to take some hydrochloric acid, and to this, I'm going to add a couple of strips of solid magnesium. Okay? There's this magnesium. So, how is the hydrochloric acid existing? In the molecular form or in the ionic form?
Before or after?
No, right now. Just this hydrochloric acid. How's it existing?
Hanging around.
Are they ions or the molecular form of HCl?
Ions.
The strong acid, right? It's existing as hydronium ions and chloride ions. Okay? Now, the magnesium. Magnesium is just elemental magnesium. So there's a bunch of rules that exist when you do redox reactions. The first and most important rule is that when you have the elemental form of anything, oxygen, hydrogen, nitrogen, xenon, doesn't make any difference. The elemental form of anything has an oxidation state of 0. Okay? That just means that there's not an imbalance between the St. Bernards and the Chihuahuas. So when you see the elemental form of a substance, that's going to be 0. Cool. So I've got H+, which if you think about it, and we've talked about this, we spent a lot of time talking about it. This is nothing more than a single proton. Okay, that's it. It is a single proton. That's it. There's no chihuahuas associated with it. It is a single proton. And then over here you have chlorine with its 17 protons. And it has, orbiting around that, a total of 18 electrons. And I know that because chlorine has an atomic number of 17. So it has 17 protons and 17 electrons. 17 St. Bernard, 17 chihuahuas. It wants to look like argon, the noble gas to the right side of it. So chlorine has already taken in an electron. Okay? So the chlorine's sitting there going, cool. Basically, it took a proton, that one chihuahua, from the hydrogen, and that came over there and is now part of the chlorine. So the hydrogen's sitting there going, I kind of feel a little bit lonely right now. Single proton. I got no chihuahuas. It looks around and sees all the other atoms. You guys got chihuahuas. I haven't had any chihuahuas. You're a little bit left out at this point. Chlorine's sitting there going, I got a lot of chihuahuas, man. I got 18 of these chihuahuas. Proton's gone too. But it can't take the electron back from the chlorine. Okay? Chlorine says, hey, one and done. You lost it. It's mine now. You took the hand off the chihuahua. I've got it. I'm not going to give it back. Now, along comes the magnesium. Okay, so magnesium here is in group 2, atomic number of 12. So it has 12 protons and 12 chihuahuas. Now, it's also important that you understand the electron structure. So magnesium, if you want the shortcut version, you go to the noble gas in the row up above, you've got neon. Okay? And if you count down, they're not listed here, but you can count down. Hydrogen is row 1, lithium like is row 2, sodium is row 3. So the numbers, they're not there, but if you count down, that tells you what energy level the valence electrons are in. So if you look at magnesium, magnesium has an inner core of neon, okay? So its inner core electron structure is neon, which is a noble gas. But then it's got, if you count down, 1, 2, 3, go over 2, so it has 3 S2 chihuahuas, okay? Out there, long way away. So neon has that core of 10, magnesium has 12. So magnesium has 12 protons, this structure. And they've been through a lot. To make magnesium is not easy. If you said, hey, let's go make some magnesium, cool. That's tough. Because you got to get 12 protons, which don't like each other, crammed together, and then you got to throw some neutrons in there to balance this whole thing out. So it isn't like, oh, we'll just like put in a vice and we'll squeeze the protons together. You have to make magnesium in a dying neutron star. Okay? Stars have to collapse to make magnesium. It's the only way they're going to exist. So this bit of magnesium, all these magnesium atoms that made this up, at some point were in a collapsing star. They got kicked out into the universe, got recombined. They ended up here on our rock. We figured out a way to separate the magnesium from all the other myriad of atoms that exist in the world. And then we said, oh, let's make it into a magnesium ribbon. Okay? What?
Is it possible to have a furnace like so hot and so much pressure to create like gold? Do we have that yet or no?
No. Oh God, no. That's from like 2 neutron stars colliding.
Oh,
Very violent.
so too much of a life.
Oh yeah, that's
Okay.
so these have been through a lot, and it's stable. How do I know that this is stable?
It's not dissolving your hand.
I'm holding it in my hand, and the bond that holds them together is pretty strong. Now, it isn't like Iron Man strong. Like I can take my fingers and just tear this apart. Okay?
What if you're just really strong?
Huh?
You broke the bonds.
Yeah, so I broke the bonds that hold the magnesium together, right? But I've separated them. But so it's strong enough to hold it together as a solid, but yet there's some flexibility to it, like I can bend it, I can tear it apart with my hands, right? But here's the point. These have been through a lot, and it's stable, okay? So now, this is where the magnesium gets a little upset. So the magnesium has these 2 outer cell chihuahuas, okay? Floating around out there. And we're going to introduce this to a single proton, to that proton, that one thing, that H+, which is nothing but a single proton. Now the chihuahuas that have been with the magnesium through the collapse of a dying star, kicked out into outer space, reconfigured into Earth, mined, put through a press, gone through this, been sitting in that lab drawer for God knows how many years, and here we are. And now I'm going to take this and I'm going to put this in with this hydrochloric acid. So the chihuahuas have to make a choice. Do we stay with the nucleus that brought us here, or do we jump ship and go with the hydrogen? That's the choice that it needs to make, okay? And it's a decision. It's a tug of war. The single proton, and that's just a single proton. There aren't 12 of them, okay? The magnesium has like 12 protons pulling on those electrons. The proton, it's just one, okay? It doesn't even have a neutron, man. It's just a single proton. And the chihuahuas have to make a choice. Now, if we want to figure this out, what's going to happen? We drop this in, okay? And right away, we see lots of bubbles. So, what's happening?
Hydrogen gas.
You're producing hydrogen gas. And I know that I'm producing hydrogen gas because it's less dense and it's floating up. And I'm going to collect that. That's gross. This one, collect that. Okay? So, here's what's happening. The chihuahuas, those 3s2 chihuahuas, they're going, hasta la vista, deuces, I'm out. I'm going to hang out that single proton. And the magnesium nucleus is going, dude, it just feels betrayed. But, Mother Nature's a lazy prima donna. Mother Nature's a lazy prima donna. So why is Mother Nature allowing this to happen? Why is Mother Nature allowing this reaction to happen? That's part of it. Mother Nature is a lazy prima donna.
Because they want to get to like the octave state or whatever, the 8th thing, right?
Yeah, Mother Nature wants to go to, which is that electron configuration. Mother Nature wants to go to the lowest possible energy state. She wants to chill out with her tie-dye dress, Birkenstocks, hitting on a hookah pipe. Okay? And so if this reaction happens, it's because she's going to a lower energy state. Now, this is what's known as a spontaneous reaction. So, I want to do this, and then, hold on. I need you to hold that light. Like that. Come on. Have you never lit a cigarette? Come on. You
got you, Bert.
Rachel, you gotta spin
Hey,
it.
Bert,
I know how to use
I had
Yeah.
a cigar the other day. I got you.
Okay.
Okay, keep
All right. Somebody light me up.
What?
Ah.
Legends jail.
Okay, so now I've got a flame. And then I'm going to put this. Okay. Whoa. Okay, that was loud. That was a good one. Okay. So now we started a second reaction. So I collected that hydrogen gas, right, in the test tube up here, and it had to react with something, right? What did the hydrogen react with? Maybe the oxygen in the air. Just throwing that out there as a radical concept. Okay. And what do we get out of that reaction? Make it rain. Okay? We're going to make it rain. A lot?
No.
No.
Very little.
Balanced equation?
No.
No. To balance it, what are we going to do? Two here and two here. Now, is this a redox reaction?
Yeah.
Yes. Because what's the oxidation state of hydrogen? Zero. What's the oxidation state of oxygen? Zero. Okay? So you have the elemental form of these substances, hydrogen and oxygen. I want to make water. So and we'll spend more time talking about this reaction in terms of thermodynamics. So basically what happens is that the hydrogen and the oxygen are up at the top of the roller coaster. And what the flame does is that it pushes the hydrogen and oxygen over the top. Okay? It provides the energy to start the reaction. And then it goes woo all the way down here. And you end up at that lower energy state of water. Okay? And it gave off some heat, it made some noise, whoo, made the test tube bark. That's the term for hydrogen when you do that. It makes the test tube bark. So we took hydrogen and oxygen, and again, all we did was rearrange the chihuahuas. So chemistry is nothing more, and redox reactions in particular, are nothing more than the study of rearranging the chihuahuas. That's it. That's chemistry. What do you do with the chihuahuas? So if you look at this from a redox perspective, let's go back to the hydrochloric acid. Let's start with that. So you had a proton and chlorine and the elemental magnesium. Okay? So the magnesium, over a period of time, is going to dissolve. Okay? So this is going to be important. One way that you can tell if a redox reaction took place is one of two things. Either you produce the elemental form of the substance, because to exist as an ion or combined with something else, it has to have an oxidation state other than zero. So if you see something that's not in its elemental form, but end up in its elemental form, then you know it's either gained or lost electrons. Okay? Now, the other thing is if you see something in its elemental form, like that piece of magnesium, and you see it dissolve, that means that's also an indication of a redox reaction, because you cannot have the elemental form of a substance dissolved in a solution. It can only exist as ions. So here's what happens.
Hey, let me eat in peace, dude.
That was him. Why are you looking at me?
Is your water bottle?
But it's out against fish.
I will take credit for that one. That's mine.
You own it? Okay. So the Chem 1 version of this reaction, if you were in Chem 1, would be, hydrochloric acid, and you get magnesium chloride and hydrogen gas, and you balance it, and you put a 2 there and go, yay, we did chemistry. Woo! Okay. Right? Now, that's the Chem 1 version of this, but it really doesn't tell the story of what's happening. You're going to make magnesium chloride. Is magnesium chloride soluble or insoluble?
Soluble.
Soluble. Why?
It's the metal and yeah.
All chlorides are soluble except for silver lead, and magnesium is not silver lead. So here's what's going to be important. This is going to exist in that solution as magnesium ions and chloride ions. Now, we made hydrogen gas, H2. Okay? So, to do redox reactions, one of the most important skills you have to have is the ability to assign oxidation numbers to the elements. Now, sometimes the oxidation numbers actually indicate electrons that are lost or gained. So if you look at magnesium here going from 0 to 2 plus, that actually means magnesium lost 2 electrons. If you look at chlorine going from elemental chlorine into a chloride ion, that has a charge of 1 minus, that actually lost that. Where it gets sketchy is when you're dealing with the nonmetals, especially like sulfur and oxygen and carbon, okay? Those tend to be a little bit sketchy because they can have different oxidation states depending upon where they're bound with. So a lot of times the oxidation state will actually tell you, hey, this is the electrons lost or gained, but not necessarily. Sometimes it just works as an accounting trick. Like, hey, we say carbon has an oxidation state of +4. That doesn't really mean that it lost 4 electrons, but we assign it that value because it makes the math work out. Okay, so here's the story. So magnesium went from an oxidation state of 0 to an oxidation state of 2 plus. Okay? So did it lose chihuahuas or gain chihuahuas? Lost it. Okay? Magnesium lost 2 chihuahuas. And these are redox reactions. So what does that mean?
Oxidation.
Something had to gain it, right? The electrons just can't disappear. Electrons have to go somewhere. Who took in the chihuahuas? Not the hydrogen.
The chlorine.
No.
The magnesium.
No.
Hydrogen gas.
Not the hydrogen gas.
Hydrogen atom.
Not the hydrogen.
Hydrogen proton.
The hydrogen proton did.
Oh,
Okay.
boy. 1 for 5.
Yeah.
We got there eventually.
If we threw enough chemistry words out there, one would stick. We'll get there eventually. Really. Okay? So it was the proton, the hydronium ion, that took in the chihuahua. So the proton's going, not lost. And the chihuahua's out there going, man, I feel a stronger bond than with the other magnesium with a nucleus that I've been with. So it jumped ship. Now, and here's where it gets a little bit weird if you think about it. So here's that single proton, which is a diamond. Okay, it's very, 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 very small. And along comes this chihuahua, and it's running around here, right? But now, that by itself isn't stable either. Because, and I can say this again because I grew up with 3 older sisters, it's like a girl going to the restroom at prom. They don't go by themselves, they go by pairs, okay? And it's the same thing with the hydrogen. So this is why I call them the diatomics chicks. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, okay? They always go together. So hydrogen by itself isn't stable. But if you take another proton and another chihuahua, then it becomes more stable. And that's why it exists as H2, which really doesn't make any sense either if you think about it. Because what do you know about those 2 protons? Repel or attract? They repel. They don't want to be near each other. They want to go flying apart. What do you know about the 2 chihuahuas? They don't like each other either, okay? So you have the 2 protons that don't like each other, and you have the 2 chihuahuas. They don't like each other either, okay? They don't want to be near each other. But yet we make hydrogen gas because the overlap of those orbitals, of the chihuahua orbitals, creates a more stable arrangement. And if you go to this idea that, hey, why does a reaction take place? Because Mother Nature gains something from it. So hydrogen exists as a diatomic because it produces a more stable arrangement than the individual hydrogen atoms by themselves. So if you look at any reaction taking place, we're going to get into what's called spontaneous reactions. So a spontaneous reaction occurs because Mother Nature gains something from it. Okay? That's the whole idea. Okay, so the magnesium went from an oxidation state of 0, because that was the elemental form of it, into 2 plus. The hydrogen went from 1 plus, a deficiency of chihuahuas, to an oxidation state of 0. Okay? So which element lost the electrons? Magnesium. So magnesium lost 2 chihuahuas. So was magnesium oxidized or reduced?
Oxidized.
Because it lost 2 electrons. The H plus, not the hydrogen, not hydrogen gas. It was not hydrogen gas. It was the proton that gained an electron. So that was reduced. Okay? Cool. What we got? Some people like a visual approach to this. If you look at it in terms of like a number line, and I'm just pointing this out because some people like a visual way to look at this. So here's your possible oxidation state. 0, +1, +2, +3, -1, -2. Okay? So the magnesium started at 0, okay, and it ended up at 2+. So if you're a visual person, the magnesium started here at 0, and it moved to the right, and it ended up at Mg 2+. Now, what did the hydrogen do? What did that proton do? It started out at 1+, and it ended up at, so it moved in the opposite direction. Okay? So if you're a visual person, here's the story. If you have one thing moving to the right, meaning that it's losing electrons, something has to move to the left to make it gain this electron. Okay? Now, let's look at the second reaction that took place. The hydrogen reacting with the oxygen to produce water. So one of the absolute golden rules, this is one of the anchors of figuring out oxidation state, is that oxygen, if it's bound up with something, unless you're specifically told something different, which is a rare exception, oxygen has an oxidation state of 2-. Okay? And that's cool. The reason it has that is because it has 6 valence electrons. It wants to get that noble gas arrangement. It's going to gain 2 electrons to be like neon. Okay? So oxygen is always 2-. The one exception to that is if you have hydrogen peroxide. If you have hydrogen peroxide, then the oxygen has an oxidation state of 1-. But unless it's hydrogen peroxide, oxygen is 2-. Now, think about this. The hydrogen reacted with the oxygen. Why did we make water and not hydrogen peroxide? Hydrogen peroxide would have made this equation much easier to balance.
Isn't hydrogen peroxide very unstable?
Yeah. Okay. What is Mother Nature going to produce?
Water.
The least stable or the most stable? Mother Nature is going to produce the most stable form out of this. And Mother Nature, whenever, under any circumstance, you're combining hydrogen and oxygen, you're going to make water, unless you are specifically making hydrogen peroxide. Now, if hydrogen peroxide was the more stable form, great. What would the oceans be full of? Hydrogen peroxide. Okay? Oh, you got to cut. Oh, run some water over it. It's hydrogen peroxide. It's cool. It'll bubble. Okay? And if hydrogen peroxide was the most stable form, we wouldn't be here having this discussion, because hydrogen peroxide is not very polar. Water is. Stuff really wouldn't dissolve in hydrogen peroxide because it's stable. Water has a very negative and positive. So, thankfully, we make water. Now, so oxygen goes from an oxidation state of 0 to an oxidation state of what?
-2.
-2. So did oxygen gain chihuahuas or lose chihuahuas?
Gain them.
Gained them.
Reduction.
Okay? So the oxygen was reduced. Hydrogen did what?
The opposite.
It lost electrons.
Oil.
Because hydrogen went from 0 to 1+. Now here's the bad part of it. And this is why the magnesium is just going to be upset. Because the magnesium is sort of going, dude, you just took away my chihuahua. And you made hydrogen gas. And you talk about a brief romance. So, let's make hydrogen gas. Run away with me. And we'll be forever together. And then all of a sudden, Boom, I introduce the flames, like, oh, lost them again. Okay, you had them, now they're gone. Sorry. Okay, now you're going to go hang out with the oxygen. Sorry, trading you off. We don't want to go along anyway. Two conflicting personalities. So the hydrogen that you just took the electrons from the magnesium, and then it goes up to the oxygen. The oxygen goes, hey, hook up a brother. Okay, fine, you can have them back. And now the hydrogen is activated as protons again. Like, well, that was briefly lit. So the hydrogen, oddly enough, then got oxidized because it lost the electrons. Okay? Now, the other big term that you need is reducing agents and oxidizing agents. Okay? So this gets a little bit confusing, but if you go back to the origins, it kind of made sense. So the reducing agent contains what is oxidized. And the oxidizing agent, oddly enough, oxidizing agent contains what is reduced. So in this situation, you have hydrogen and you have oxygen. What's the reducing agent and what's the oxidizing agent? H2 is what's oxidized. So the hydrogen is the reducing agent. Oxygen, though it is reduced, is the oxidizing agent. Okay? And oxygen was the basis of this, and that's why it's called the oxidizing agent, because that comes from the word oxygen. Okay? And so oxidizing agents, we just kept them as a generic term. So oxygen is very easily reduced because it really wants to take in two chihuahuas. So since the oxygen is very easily reduced, that's where the word comes from, because it's an oxidizing agent. Now, we obviously want to keep these things away from each other in the storeroom. So if you look at the storeroom, we have oxidizing agents on one side, we have reducing agents on the other. Because of the fact that if you put them together, you get a reaction. You get a quick rearrangement of the chihuahuas. Okay, so the next thing I'm going to hand out, this is not due, we're just going to talk about it. Don't flip out. If you want to stand up and stretch, this is a good time. Mark, can you shut that off for a second?